Welcome back to Chemistry 30. This is the MS1.7 section, the VSEPR model, or valence shell electron pair repulsion model. So here we'll be able to describe the three-dimensional shapes of molecules using the VSEPR model and determine the electron domain and molecular domain of a given Lewis structure. So we kind of touched on that in that little lab that you did, in which we looked at different shapes from a three-dimensional point of view. So now we will continue with that. So the shape of a the shape of a molecule has quite a bit to do with its reactivity. This is especially true in biochemical processes, where a slight change in the shape of a three-dimensional space might make a certain molecule inactive or cause adverse side effects. One way to predict the shape is using the valence shell electron pair repulsion theory or model. The basic idea behind this theory is that the electron pairs surrounding a central atom, whether involved in bonding or not, will try to move away as far as possible from each other to minimize repulsion. So I often like to talk about when people go in an elevator, they tend to go as far away from each other as possible, as opposed to being huddled up in a corner, which would be weird, wouldn't it? Simply put, electron pairs, whether they may be bonding or not, repel each other. By assuming that electron pairs are placed as far as possible from each other as they can, then we can look at the shape. So just like in that little simulation that you did, if you twist the molecule, turn the molecule, eventually it goes back to its most stable state in which everything was repulsed from each other. Two geometries can be determined. The electron domain geometry, in which all pairs, whether they're bonding or not, are considered, contributing to the shape. And then we have molecular geometry, in which the non-bonding ones become invisible and only the bonding ones are considered. For the purposes of geometry, double and triple bonds count the same as single bonds, so in terms of repulsion. So if we look at this first example, how many electron domains and molectron domains are found around the central atom A? So first of all, we have to identify the domains. And of course, domains, as mentioned in that activity that we did, domains we can think of areas where electrons can be found. Okay, so that's the first part, the number of domains. So if we look, we will see that there are some domains here. Here we have a domain here where there is a bond between the A. Now, of course, I should add one extra thing here. Around, usually we're talking about around the central atom. So we have a single bond, and that's considered a domain around A, where there's electrons. Above the A, there's a domain. Over here, there's a domain. And here's the domain. So there are actually 4 domains around A where I can find electrons. So you have to be able to identify that. So if I look at electron domains where bonding and non-bonding are considered, there are 4 electron domains. And by that we mean there's 3 bonding and 1 non-bonding domain. So there's 4 electron domains. And if we look at molecular domains, so we just consider the bonding ones. But of course the non-bonding one is still contributing to the structure shape, but we just simply don't count it. All right, so key thing, how to figure out domains, the areas around the central atom where electrons can be found, whether they're non-bonding or bonding. Electron domains consider the bonding and the non-bonding, whereas the molecular domains only look at the bonding. All right, so moving on to domain geometry now. So once we know how to figure out domains, we can figure out the geometry that's involved. So to determine the electron domain geometry, all one must do is count the number of electron domains in the Lewis structure. That geometry will be the number of electron domains. So if I look at the ammonia molecule, it's very similar to the molecule in the previous page. I have 3 bonding and 1 non-bonding. So just like when we did that activity, what I like about it is that it shows that the lone pairs or the non-bonding, they kind of showed it as a big bubble or a big balloon, indicating areas where those 2 electrons can be found. And it actually takes up more room than, let's say, a bonded atom. So here we have 1, 2, 3, 4. We have 4 areas around the N. So there are 4 electron domains. Therefore, if all 4 are contributing to the shape, of course, that is going to be the tetrahedral shape that we talked about earlier. Okay? So tetrahedral. If we look at, let's highlight that. That is electron domain geometry. So we consider all of those domains, whether they're non-bonding or bonding, as important and contributing to the shape, tetrahedral. Determining the molecular geometry. The electron domain geometry is often not the shape of the molecule. The molecular geometry is that defined by the positions of only the atoms involved in the molecule and not the non-bonding. So if we take a look at that, ammonia still has that lone pair, but we kind of cover it up and don't look at it, and we just simply look at this. And we'll see that that is a trigonal pyramidal or trigonal pyramid type shape. The trig stands for 3 sides, and the pyramid, of course, means it's a little pyramid. So you can see the 2 different types of geometry yield 2 different results. Tetrahedral, if we consider everything, bonding and non-bonding. But if we're just looking at the things that are making the bonding shape, we can see they're repulsed. We know that there must be something up here pushing things downwards, but we don't consider it. We just simply look at the shape. Within each electron domain, there may be more than 1 molecular geometry. So if I start off with tetrahedral, if I remove that 1 atom and I get that trigonal pyramid shape, I know that there still is a lone pair up there, but I'm only looking at this. If we take away another atom, yes, we know there's a lone pair here and a lone pair here, but what our eyeball see is a bent shape. So that is referred to as a bent structure in terms of molecular geometry. So with that, we'll kind of look at all the scenarios that we could end up with here. So first of all, we'll look at 1 bonded to 2, a central atom here bonded to 2. And of course, when the one shape we can get here is linear. So when we have 2 domains, 2 areas around that central atom, it can make a linear shape. That's the only one it can make. We'll see that the bent shape comes into play later on here. Okay, so 2 domains makes up a linear shape. In the linear domain, there is only 1 molecular geometry, and that's linear. If we just had 1 domain around that central atom, that is also considered linear. But in that case, of course, we don't look at a central atom. We just look at 2 things simply bonded together. If I look at something that has 3 areas around the central atom where we could have bonding or non-bonding, that is referred to as trigonal planar. So if they are all bonding, trigonal planar. If I take 1 away and leave it as a lone pair of electrons, then of course we would only see this. It's the bent shape. Okay, so there are 2. Now, the electron domain geometry is always going to be the first one here. If we consider all of these important, trigonal planar is the electron domain geometry. But looking at the molecular geometry, there's 2 different cases. Trigonal planar, if all electron domains are bonding. Bent, if one of those domains is a non-bonding pair, such as we see here. Now, a word about a non-bonding pair and bond angle. As I mentioned earlier, non-bonding pairs take up more room than bonding. Therefore, their repulsions are greater, and this tends to decrease the bond angle. So, if I look back over here, if I have a tetrahedral shape and all of them are bonds, 109.5, 109.5, etc. But if I was to take that H away, for example, in an ammonia molecule, notice that it's no longer 109.5. It's like this has repulsed cause these to squeeze together to make a smaller bonding angle. If I take away another hydrogen, there's further squeezing in here, making that bond angle even smaller still at 104.5. And also, if we look at multiple bonds and bond angles, double and triple bonds place a greater electron density on one side of the molecule because there are more electrons there, and they also affect bond angles as well. So you can see instead of 120, 120, 120, this double bond here causes a greater repulsion, squeezing this angle closer together.